Hello to everyone. I'm Julian Genovese, data scientist in Data+AI. And today we're going to talk about Graph+Science from classical machine learning to deep learning. What is the reason for this speech? The reason is that usually we have a lot of speech that are very technical, but sometimes we didn't get the entire path in the graph data science. So what I want to do is to start from the beginning, so classical machine learning, and I want to arrive to deep learning. So what we will see today is a brief introduction to graphs. We will see what is graph machine learning, so the classical approach. We move on to knowledge graphs, and we will finish with graph neural networks and the conclusions. Let me do only a brief introduction about Data+AI, because I worked on graph data science in this company. And what is the reason? The reason is because we are a big data company focusing on big data, artificial intelligence, quantum computing, and we have a lot of projects in several industries and several business with more than 90 projects already derived in production. But let's move on to an introduction to graphs. Okay, I know that a lot of you already know graphs, but I want to give a total perspective on this topic. So, in general, a graph is a mathematical representation of complex and connected entities that we call networks. So we have nodes that are the main elements of a graph, as we know, that are entities or objects of the real world. We have links that represent the relationships, the connection between entities, the labels that represent the category of a node, for example, the fact that you are a person, you're a book, or whatever you want. But what I want to emphasize is the properties, because they enrich the nodes or the relationships with some information. But the main point is you don't have a fixed schema. So this is the main improvement of graph. The classical improvement of graph. So you don't have a fixed schema. So the reason why we use graph, as you know, are mainly three. Because they capture interactions. So this is quite obvious because this is a unique model that take into consideration the relationships between data. Because as you know, sometimes they are very important, very fundamental. So you don't have to waste them. The second reason is that they are visual. So this is very important in a bank case because you need to know what your algorithms are doing. So you are not interested in black boxes algorithms. And the last point is graphs are dynamic. So you don't have a fixed structure or schema. So you can answer changing questions and changing queries. Okay, so when you can use it with some recommendation engine, but working using, for example, community as well, community of customer as well, that you cannot catch with classical machine learning algorithms. You can work on anti-fraud, that they are relational by nature, involving different kind of people, and with bill of materials, because maybe your supply chain or your materials can be visualized using the graph. And so you want to understand what is the robustness of your supply chain or your set of materials. So these are three main examples. But the focus today was not to understand the difference between classical machine learning and graph machine learning. The focus here is to understand the modern approach. So let's start from the classical one, the graph machine learning approach. In this case, we work on three main category of algorithms. The community detection one, where we detect a group of cluster of nodes. The centrality, when we understand the importance of the nodes in the network, but finding where we find optimal path between two nodes. Link prediction, where we estimate the likelihood of new relationships, and similarity. So to understand how alike two nodes are. But the very, very important point is that all these algorithms work on the topology. So you have to remind this part. It is because it's the main part, the main point to understand the migration to deep learning. So I don't want to spoiler what we will see later, but I want to explain a little bit these algorithms. So let's start with the community detection one. In this case, the community detection one, you want to understand if, what are the community in our networks, and if our node belong to one of these communities, and what is the community. And we have different approaches. For example, we can understand, for example, the different densities of nodes in the network using the clustering coefficient. So the more connected are the neighbors of a node, the higher will be the clustering coefficient of a node. But sometimes you can be interested in the island, the several islands of in a network. So nodes that don't interact with other nodes. So you can use the strongly or the weakly connected components that are two variants of this approach. Or you can use a label propagation approach. In this case, you're working with a semi-supervised approach. So in what sense? That you have some labels, and you want to see how this label will spread into your network using the topology. So you start from an initial state with only some label, and you finish with a lot of other labels based on your topology. After that, we have the centrality approach, the centrality importance. In this case, we want to focus on a certain kind of importance that you have to define, is the central point. You have to define an importance based on what you want to catch. So we have different definition of centrality. But as you can see, they are all based on the relationship. Okay, so you have the main centralities are a degree between page rank that maybe you know, but as you can see, they are based only on nodes and relationships. After that, you can work on pathfinding and search. In this case, your focus is on what is maybe the shortest path between a point A and a point F, based, I don't know, on a weight. Okay, so you have different weights between your nodes, and you want to understand what is the path with the shortest total weight. Okay, so you can have different approaches, different objectives, but in this case as well, you are focused on nodes and relationships. After that, you can start and study the similarity of two nodes. Okay, so in this case, the main point is that you want to understand the similarity using the relationship. So in this case, we have two persons, Julian and Marco, that they saw several movies, Toy Story, Matrix, Titanic, Star Wars, and The Good Father. I want to understand, in the case of Jacquard similarity, the similarity of Julian and Marco based on the movies that they have seen. Okay, so in this case, for example, Julian have seen two movies that Marco have seen as well. So in this case, it's quite obvious that they are pretty similar. In case of the Pearson similarity, you want to see the similarity of Julian and Marco based on their ratings. Okay, so in this case, if they have high ratings for Matrix and Titanic, maybe they are similar because they are the same tastes. Okay, so this is a numerical similarity, it's not a set similarity. And we can also be interested in link prediction. This is maybe one of the most important topic when you work in real context. In this case, you want to understand if two nodes can create new relationships in the future using different approach. Common neighbors, Damic Hadar In this case, if you're working with common neighbors in a social network, what you want to say is, okay, if two people like A and D have a lot of common friends, but A and D don't know each other. If they have a lot of friends in common, maybe there is it's more likely that they will be friends in the future. Okay, and I think there is another approach. You have a lot of different approaches, but they are all based on relationships and nodes. So this is the first point. Okay, it is quite is a quite classical approach. You have the nodes, you have the relationships, and it's okay. This is the classical one. But let's move on to the modern approaches. And the first improvement is the knowledge graph. Okay, so what do you do in the knowledge graph? The knowledge graph is quite simple to understand, but it's very difficult to do in practice, because in this case you want to say, okay, I want to expand our node. In this case, I don't know. I have a person called Mario that participated at a work meeting in Milan. So you can model this information in the properties of Mario. But in the knowledge graph, for example, you can model as node in a graph using different labels. For example, the event, work meeting, and the place, Milan. But the point of a knowledge graph is not to change the model, but to improve your prediction. And what is the idea? The idea is, okay, maybe we don't know where Milan is, but maybe we have a certain sense, in a certain sense, a context from I don't know. We have done web scraping. Okay, so we know that Milan is located in Italy. So you don't know the information, the Italy information from your graph, but you can infer it from a context. And this is a very important idea because it's very related on the human being-based reasoning, because you have a context related with another knowledge that you have obtained by another, for example, table or whatever you want from another silos, and you want and you improve, you increase your knowledge about your graph, Mario, or participate at work meeting in Milan using this context. Okay, so how they work? For example, you start from raw data. Okay, for example, let's start with an NLP problem where you have a text, okay, and you have some entities in this text, but you have a context as well. So you have your natural language processing where you create the entities. So you start from raw data, the text, you create the entities in the second step in the natural language processing. You build a graph. In this case, what you are doing is to create you take the entities from your starting graph. You link them with the context, and so you have created an improved graph that you can use for additional analysis. So the context in this case will be very, very important because, as you know, the same thing can mean several things based on context. So you can use the context to improve your analytics. So why use knowledge graph? The reason why you use knowledge graph is because you create this common ontology, this common knowledge on a certain topic. For example, I don't know, about football, about in general sport, I don't know, computer science. You create a common ontology, and you will use it to analyze other text about this context. In addition, in this case, you avoid data silos because your context is graph-based. So you create it once, and you don't want to join it each time that you want to predict something about, I don't know, a text or whatever you want. And in addition, the point is that the context can help you to discover new relationships, because maybe you know that a person is located in Milan, but you don't have the information of where Milan is located. So you create a new relationship with Italy. Okay, so the use cases are a lot, because as I said, you can do information retrieval. Okay, when you don't have the Italy information, you can use to discover disease similarity. You have a context, you know that from this context that two people are similar, and you can predict disease. You can use to fraud detection, because maybe you can introduce old fraud schema as a context. And so you have a lot of examples, link prediction, whatever you want. So the context, I think, in my opinion, will be the future of graphs, because they have a they are very important in a graph approach. And finally, the main point is graph neural network. Okay, graph neural networks. They are very important for what reason? They are very important because now the point is they combine graph topology with node features. Okay, this is very important. This is the main point, because in the previous approaches, if you want to use the node features, the node properties, sometimes if you want to use them, for example, in PageRank, whatever you want, you have to model them as other nodes, other relationships. In this case, the GNN use the graph topology, combine them with node features. So in a way that you come back to a classical graph. For example, you have a node of different person, okay, but you can use the features as well. This is the main point, the very important point. This is the reason why the GNN exists, and so it's very, very important. And the other important point is they are not the graphs are not images or text, so you cannot use the classical approaches, because the graphs have no fixed form. They have variable size, so you have to create something different. So you cannot use classical traditional deep learning techniques. I wrote a Medium article about this fact. And how do they work? The idea is to create something similar to images, okay, because you can imagine a picture like a fixed graph, okay, with a fixed number of nodes and relationships. So you can use something similar. The idea is to aggregate information from the neighbors of a node, okay, with a mean or something like that. And this aggregation will be embedded as in NLP, okay? And so in general, the embeddings will encapsulate the local properties of the graph. And we can use it for a lot of tasks. The point is that we can take information from one op away, two ops away, and so on, based on your problem. So you have to tune these parameters. So what is important, the local neighbors with respect to the global neighbors. So the more path, the more ops you take, the more important will be the total graph. So you can use edge classification, regression, use cases are edge classification and regression in this case. So because it's very easy to do it with graph neural network. You can also do node classification and regression, link prediction. But in addition, that is one of the main improvements, you can do graph classification. You can classify a graph. What is the common application of graph classification is in, for example, cybersecurity, because each day you can have some links between I don't know, between hosts. And maybe each day you have different links, different relationships. You want to understand if this can be related with certain sense an infection of your computer networks. Okay, so this is a real case, a real business case. So the question is, okay, we have seen that graph neural network take the node features, take the topology, so they take all the information. So we can use graphs for everything. Okay, so the answer is we can use graphs for all kind of problems that involves a group of entities that interact among themselves. So this is the classical answer. And for all the problems where we have dynamics or complex schemas that change all the time. And sometimes if you, for example, don't use graph neural network, you can use graphs for visual analytics and human explanation. Sometimes they are not, graphs are can be not the best solution because maybe you don't have relationships. So graph neural networks and all the graphs approaches maybe are not the best solution for your problem because you are not in a graph. But if you are in a graph, you can improve your business problem a lot with all these approaches. So the conclusions are, in general, that graph, in my opinion, are the future because you can blend various datasets into a structure that enables to reveal connection between otherwise that are otherwise are impossible to catch. You can discover information that are relationship-oriented models. Okay, and the point is that we don't only have the classical approaches as we have seen, PageRank, whatever you want to, but you have some modern approaches to improve all these tasks. Okay, and so the point is that you already have a lot of connecting information. So the main user problem is, do you have the data to solve your problem in that way? And the answer is yes, you already have this kind of data. So the point is, it's time to use graphs. And it's time to use graphs with classical graph machine learning, knowledge graphs, and deep learning. Guy, thank you. And if you have some other questions about this topic, how can you start with graphs? Text me on LinkedIn, or you can text me on my email, and you can see my articles on graphs on the Data Reply Medium page. So thank you, and see you the next time.